Hi, everybody. It's Professor Mitchell, continuing with Chapter 10. Today, we're looking at Section 10.7 on power series. So to introduce this section, we're going to do a little graphing calculator activity. I am going to look at or I should say, we are going to look at the graphs of these four functions. Y1 equals sine x, Y2 equals x, Y3 equals x minus x cubed over 6, and Y4 equals x minus x cubed over 6 plus x to the 5th over 120. So I'm going to switch over to my calculator. All right, so you can see I've entered those four functions on my calculator app. So this green plus sign next to Y1 means that Y1 is going to be up on the screen, but for now I've got Y2, Y3, and Y4 turned off. So if I hit graph, you see the familiar graph of Y equals sine x. Now I am going to go back into the Y equals screen and I'm going to turn on the Y2 graph. So I'm going to compare Y1 and Y2. And when I go back into the graph screen, you know what the graph of Y equals X looks like. Really doesn't look a whole lot like the graph of Y equals sine X overall, except notice that near X equals 0, that line passes very, very closely to the graph of Y equals sine X. You may remember from Calc 1, every function, every differentiable function has what's called a linearization. So this is a line, a straight line that does a good job of approximating the function near a particular point. And Y equals X is the linearization of Y equals sine X at X equals 0. So near X equals 0, X is a pretty good approximation for sine X. So now I'm going to go back into the Y equals screen. I'm going to turn off Y2 and I'm going to turn on Y3. I go back into the graph window. And now you can see I've got this third degree polynomial, which from about here, looks like that's maybe x equals -1 to about x equals 1, does a very, very good job of approximating sine x. Again, near x equals 0. And finally, if I go back into the Y equals screen and turn off Y3 and turn on Y4, now we're going to have a fifth degree polynomial, which does an even better job of approximating the function Y equals sine X from practically x equals -2 to x equals 2. So the idea is that if you keep doing that, as long as you don't mind having a higher and higher degree polynomial, you'll find a polynomial that does a really, really good job of approximating the values of Y equals sine X. All right, so switching back to the presentation. All right, that brings us to the idea of a power series. A power series about x equals 0 is a series of the form sum n equals 0 to infinity of c sub n x to the n, which is c sub 0 plus c sub 1x plus c sub 2x squared plus blah, 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 plus c sub n x to the n, continuing on and on forever. So this is an infinite series. And then a power series about x equals a is a series of the form sum n equals 0 to infinity of c sub n times x minus a to the n. So the same idea as what we had up here, except that all of the x's have been replaced with x minus a's. The number a is called the center of the power series, and the coefficients c sub 0, c sub 1, c sub 2, et cetera, are constants. I like to think of a power series as an infinite degree polynomial. All right, so in this first example, we are going to look at for what values of x do the following power series converge? And you can see those power series here, along with a little hint of the solution. So for each of these power series, we're going to answer most of this question by using the ratio test. It's not going to answer the complete question, but it'll come pretty close. So now I'm going to switch over to the tablet. All right, and here we go with letter A. So the sum n equals 1 to infinity of -1 to the power n minus 1 times x to the n over n. So again, we're going to use the ratio test. Remember, the ratio test looks at the limit as n approaches infinity of absolute value a sub n plus 1 over a sub n. So in this case, that absolute value does make a difference. All right, we're going to have -1 to the n plus 1 minus 1, which is just n, times x to the n plus 1 over n plus 1. And then as usual, instead of dividing by a sub n, we'll multiply by the reciprocal of a sub n. So that'll be times n over -1 to the n minus 1 times x to the n. All right, so what that absolute value will do is really it'll eliminate the powers of -1. I mean, even before I apply the absolute value, there's just the single -1 left in there. And when I divide x to the n plus 1 by x to the n, I just get x. All right, so we are left with the limit as n increases without bound. So now I can ignore the -1, and I'm going to have the absolute value of x times n over n plus 1. Now x does not depend on n, so I can pull the absolute value of x outside this limit. So I'm left with the absolute value of x times the limit as n increases without bound of n over n plus 1. That limit is equal to 1. And so the limit we're looking at is the absolute value of x. So at this point I say, okay, what was the question again? I was using the ratio test. Remember that the ratio test gives you a number that we call rho. And whenever rho is less than 1, your series converges. It actually converges absolutely. And I think in this question, all they asked was, when does it converge and when does it diverge? So by the ratio test, this series converges when the absolute value of x is less than 1. It diverges when the absolute value of x is greater than 1. So that just leaves one unanswered question, which is what about when the absolute value of x equals 1, i.e., when x is positive or -1. Okay, because in that case, rho will be equal to 1. And in that case, the ratio test is inconclusive. So what you have to do in this case is look at those values individually. So let's start with x equals 1. Let's see, when x equals 1, this series just becomes the sum n going from 1 to infinity, -1 to the n minus 1 times 1 to the n over n. Well, 1 to the n is just 1. So that's going to give us the sum n going from 1 to infinity of -1 to the n minus 1 over n. All right, so we have looked at this. We've seen this series, I think, at least once before. If you write out the first few terms of this series, you get 1 minus 1/2 plus 1/3 minus 1/4, et cetera, et cetera. I sometimes call this series the alternating harmonic series. And this series converges. It converges conditionally. And the test that you use to determine that this series converges is the alternating series test. I will leave out the details because we've talked about those before. All right, so now we just look at x equals -1. I'll start that down here, and I'll probably need to go up top again. Let me get rid of some of this scribble down here. Okay, the sum n going from 1 to infinity, -1 to the n minus 1 times -1 to the n over n. Well, -1 to the n minus 1 times -1 to the n is -1 to the 2n minus 1. And what's special about 2n minus 1 is that it's always odd, right? So if you raise -1 to an odd power, you just get -1 all the time. So this series is just sum n going from 1 to infinity of -1 over n. And that is just the harmonic series with every single term turned negative. Okay, or another way to look at it is if you pull the -1 out here, sum n going from 1 to infinity of 1 over n, this series here without the negative is the harmonic series. And we know that that series diverges. And if you just stick a -1 in front of a divergent series, it's still a divergent series. All right, so what we have is the following. Therefore, the original power series converges if x is between -1 and 1, including the 1. Otherwise, it diverges. All right, so that is the idea behind how you determine where a power series converges. So let's look at the next example. Letter B, the sum n going from 1 to infinity of -1 to the n minus 1 times x to the 2n minus 1 over 2n minus 1. So this would be a really good one for you to pause the video, try this one, and then come back and compare notes. I think it's pretty similar to letter A. So I will go ahead and let you do that. All right, so now hopefully you've tried this example. We're going to look at the limit as n increases without bound, absolute value a sub n plus 1 over a sub n. All right, so a sub n plus 1 is going to be negative 1 to the power n plus 1 minus 1, which is just negative 1 to the n. Now let's do this because we really need to be careful with those two n minus 1s. Remember, we're replacing n with n plus 1. So that's going to give us x to the power 2 times n plus 1 minus 1 over 2 times n plus 1 minus 1. Oh dear, I'm going to run out of room here. Okay, so I'm going to put times, and then I'm going to just put an arrow here. All right. So now I'm going to multiply by the reciprocal of a sub n. So that's going to be 2n minus 1 over negative 1 to the n minus 1 times x to the 2n minus 1. Okay, now I can clean this up. All right, just like before, negative 1 to the n divided by negative 1 to the n minus 1 just leaves negative 1. And let's be super careful with these other things. So we have a negative 1. We're going to have an x to the 2n plus 2 minus 1. So that's 2n plus 1 over 2n plus 1. And then times 2n minus 1 over x to the 2n minus 1. All right, so now x to the 2n plus 1 divided by x to the 2n minus 1 leaves an x squared. All right, so we have the limit as n increases without bound. We can ignore the negative 1 because that's going to come out in the absolute value. We have the absolute value of x squared times 2n minus 1 over 2n plus 1. And again, x does not depend on n. And also, we don't need the absolute value on the x squared because x squared is never going to be negative. So we can ignore that x squared. It turns out it's not going to help all that much, ignoring it. Okay, but the limit as n increases without bound of 2n minus 1 over 2n plus 1 is again 1. So this limit is equal to x squared. That's my value of rho. All right, so what we can determine from that is that the series converges if x squared is less than 1, which is just another way of saying x is between negative 1 and 1. And diverges if x squared is greater than 1. In other words, when x is greater than 1 or less than negative 1. All right, so again, we have to look at the endpoints. We need to look at x equals 1 and x equals negative 1. So let's get rid of all of this. And we'll start with x equals 1. When x equals 1, you get the sum n going from 1 to infinity, negative 1 to the n minus 1 times 1 to the power 2n minus 1, which is always going to be 1 over 2n minus 1. All right. So negative 1 to the 2n minus 1 is just 1. So this series becomes the sum n going from 1 to infinity, negative 1 to the n minus 1 over 2n minus 1. All right, so what is this series? Well, I think it's going to be 1 minus 1/3 plus 1/5 minus 1/7, et cetera, et cetera. Okay, so I don't have a name for this series, but this one is also going to converge by the alternating series test. That's very easy to check. It does converge conditionally, but they're not asking about conditional or absolute right now. All right, so this series converges by the alternating series test. Just a few details to fill in there. All right, what about when x equals negative 1? When x equals negative 1, this series becomes the sum n going from 1 to infinity, negative 1 to the n minus 1 times negative 1 to the 2n minus 1 over 2n minus 1. Multiply those powers of negative 1 together, and you get the sum n equals 1 to infinity, negative 1 to the 3n minus 2. So that's kind of unusual. What does that do? Well, when n is 1, that gives you negative 1 to the first, and that would be over 1, so negative 1. And then when n is 2, you would have negative 1 to the fourth over 3, so that would be plus 1/3. This is also going to be an alternating series. It happens to be the exact opposite of the one we were just looking at. This series also converges by the alternating series test. So the original power series converges on the entire closed interval from negative 1 to 1, including the endpoints. That's what closed means. And diverges otherwise. All right, well, I think the next two examples are going to go a little faster. Letter C is the sum n going from 0 to infinity of x to the n over n factorial. So again, I'm going to use the ratio test. Always use the ratio test for power series to start off with, and then you might have to do something else with the endpoints. All right, in this case, we are, well, no, I take that back. I was about to say we're not going to need the absolute value, but I do need them for the x, so I take that back. All right. Okay, so a sub n plus 1 is going to be x to the power n plus 1 over n plus 1 factorial times the reciprocal of a sub n, whoops, is n factorial over x to the n. X to the n plus 1 divided by x to the n is x. And as we've talked about before, n factorial divided by n plus 1 factorial just leaves an n plus 1 behind. All right, so we have the limit as n increases without bound of absolute value x over n plus 1. Now remember, x is a fixed number, and n plus 1 is increasing without bounds. So any fixed number divided by a number that's increasing without bound, this limit is going to be 0. Remember that the value that comes out of this limit is what we call rho. So this is kind of interesting. What this is saying is, regardless of the value of x, rho is always equal to 0, which means that this series converges no matter what. All right, and so there aren't even any endpoints to check. That's the end of the story. This series converges for all values of x. So that's a thing that happens sometimes. And finally, we have this series, the sum n going from 0 to infinity of n factorial times x to the n. So kind of like the last example, except we're multiplying the n factorial instead of dividing it. So looking at the limit as n increases without bound. Oh, look, it's actually easy to write a sub n plus 1 divided by a sub n this time. It's going to be n plus 1 factorial times x to the n plus 1 over n factorial times x to the n. All right, so n factorial, n plus 1 factorial divided by n factorial is n plus 1. X to the n plus 1 divided by x to the n is just x. All right, so we have the limit as n increases without bound. We'll keep the x inside the absolute value multiplied by n plus 1. Remember that x is a fixed number. So when you multiply a fixed number times n plus 1 and let n increase without bound, that limit is going to be infinite unless, well, put it this way. It's going to be infinite unless x is 0. And if x is 0, then the limit is going to be 0. All right, so this limit, I was about to say it doesn't depend on x, but it does, but only in the sense that if x is 0, then the limit is 0, but if x is not 0, then the limit is infinite. So the only way that this series converges is if x equals 0, which is not a very interesting scenario, but that's also a thing that happens. So the series converges only when x equals 0.